Okay, this video is going to start out with a review of what we did before, and then we're going to add some new things to it. So the first thing it says is to create a table and sketch. So we're going to create a table by plugging in the numbers into this equation. So we've got x, and then we have f of x, which we talked about last time is the same thing as y. Now, we told you what numbers to usually pick. You can pick anything that you want to, but typically these are going to be the best ones to choose. So I'm going to take -2 all the way to +2 and plug them into this equation where I see x. So the first one I'm going to do probably is 0. So 3 to the 0 power is equal to 1. That's going to be our y-intercept. Then I'm going to do the positive numbers. 3 to the first power is 3. 3 squared is 9. And then the negative exponents, remember, those turn them into a fraction. So 3 to the -1, this is a review, is 1/3. 3 to the -2 is 1 over 3 squared, which is the same thing as 1 over 9. So we are going to plot those points, and it doesn't have to be perfect. So we've got 0, 1, put a dot there, and then at 1, 3, so 2, 3, put a point there. At 2, 9, somewhere up here, doesn't matter. And then we have at -1, it's actually going to be at 1/3. So it's going to be close to the x-axis, but not on it. And then at -2, it actually gets even closer to the x-axis, but it's actually approaching a value called an asymptote. So you guys talked about this before. It was on your assignment. That asymptote is the invisible fence that this cannot cross, but it gets closer to. So asymptote. And this one is sideways. It's called the horizontal asymptote. And it's always the equation y equals, and it's the value of y that it cuts through. So this is y equals 0. If our equation had looked slightly different, so f of x, 3 raised to the x plus 1, this number on the outside would make every part of my graph shift up. So this is kind of like an additional warm-up problem here. This would have a horizontal asymptote, that's what HA stands for, at y equals 1. So if there's ever a number out in front here or out behind here, then that means it's equal to 1. Now, the additional piece for today versus yesterday is talking about the domains and the range. So we're going to look at a graph on the next page, and then we're going to kind of talk through it. So here we want to figure out what the exponential equation is from the graph, and then we'll talk about some key features. So you don't have to make a beautiful sketch, but maybe write some of this stuff down. I'm going to list it out as chart values. Okay, so I know all my points, and I'm going to just start writing the points down. So 0, 128, 164, 232, and then it skips. There's no 3. That's a lie. It doesn't skip. I just didn't see it. 316, 48, and then 54. Let's talk about some key features. The first thing you hopefully notice is that it does have a y-intercept, and that y-intercept is at 0. So the y-intercept is at 0, 128, which means the y-intercept itself is at y equals 128. You should also notice that it has a horizontal asymptote. The horizontal asymptote is always the equation y equals, and it's the line that it gets close to, but it doesn't actually cross. In this case, that's y equals 0. So horizontal asymptotes are like the invisible fence that dogs run around in the backyard. They can get close to it, but they can't cross it. All right, so we've got the table, we've got the key features, and then we want to talk about just domain and range first. Domain values go from left to right. So domain values go from left to right. Let me use my pointer tool. So this curve, even though it does curve down like this, it's asking us, is there any barrier to how far left and how far right my x values go? And the answer is no, because the arrows are going to continue to rise to the left, and this arrow is going to get closer and closer and closer to that asymptote without actually crossing it, so it continues. If there are no barriers, you can list the domain as -infinity to +infinity, or say all real numbers. Okay, so for any exponential equation, whether it be growth or decay, the domain is going to be all real numbers. The range is actually going to be slightly different. The range values are the y values. So it's looking for any barriers to the y-axis. Let me use my pointer tool again. So for the range, if you look at this, if we follow our curve, it's actually going down, and it does have a barrier. It has an asymptote as a barrier. That curves our line. So we're starting high in the air, so it can go all the way up to the sky infinitely, many places, but then it cannot cross that little imaginary barrier. And that imaginary barrier is a y value of 0. Okay, so it can go infinitely many as high up as it wants to, but it cannot cross 0, which means your y value has to be greater than 0. Not equal to it because it can't touch. That's the electric fence. You'll get shocked. Has to be greater than 0. And this is also going to be true for your exponential equations, except there's going to be some problems that may look a little bit different, but you always want to just take the sketch, look at the sketch itself, and see where is the electric fence. Then the last thing you really want to do is try to figure out what the equation looks like. So your equation is going to be f of x or y is equal to some starting value a times some value of b raised to the x power. What we're looking for is what the pattern in the numbers is, okay? The pattern between the numbers. So if you look at the numbers, it might be a little bit tough to figure out at first, but 128 to 64, that's actually being cut in half or divided by. From 64 to 32, that's being cut in half or divided by. 32 to 16, cut in half. 16 to 8, cut in half. 8 to 4, cut in half. Since it's being cut in half, that is what we call our b value or our growth factor. It's not actually growing, it is decaying or cutting by half. So that's our first start. Then we're going to have our x value stays in our equation. And then our a value is that y-intercept that we already identified. So 128. That's what your equation will look like. Okay, so establishing the key features, you need to be able to look at your domain and range, and then you look for the pattern in the numbers. Now, this one was going by division. It was dividing by 1/2 each time. If it was multiplying by, say, 2 each time, that would also be an exponential. But if you were adding or subtracting, that's not exponential. That's a linear pattern. That's what we did last semester. So make sure you understand the difference between those two things. We're looking for multiplying, or we're looking for division for an exponential growth problem. And here is the exponential growth equation. And from last video, we did say that if the b value was larger than 1, that this was a growth. This is a review. And that if it was less than 1, and actually technically between 0 and 1, this was a decay. So a growth is a whole number. Again, this is a review. And a decay was a fraction that was between 0 and 1. If the fraction's like 5/4, that's a number that's larger than 1, so that would also be a growth. So just be careful with that. So let's see if we can use our stuff to do this example. We want to write the equation given our table. So we're going to look for a couple things. Let's look for some key features. First, the y-intercept. Y-intercept is at 0, 4 because the the x value is 0. That's our y-intercept. Then we're going to look for our pattern in the numbers. So 4 to 12. Let's see. To go from 4 to 12, we're multiplying by 3. To go from 12 to 36, we're multiplying by 3. That looks great. And the pattern actually continues. Since the pattern continues in its multiplication, that means we have an exponential growth. So remember that pattern goes in the second piece, raised to the x power, 3. And then the part that goes in front is our y-intercept. So 4. We're going to put parentheses around the 3. If you wanted to check to make sure your equation is right, you definitely can, and you should. So to check our work, we're going to take an x value of 0 and plug it in. So 4 times 3 to the 0 and see if we get out 4. Okay, so 4 times 3 raised to the 0 power is 1. 4 times 1 is 4, and that checked. The next two are try it problems. You should try them, and then let me know if you get stuck. So you can write the points down, or you can just show your work on your paper if you want to try it. It doesn't matter to me. Definitely hit pause here, try it on your own, so that way you know you're doing what you're supposed to. Looks like as x increases by 1, the pattern is being multiplied by 4. So we've got f of x is equal to, remember we've got two parts, 4 raised to the x, and then the inside piece, or the number out in front, is going to be your y-intercept. So let me just make sure we know this. You are not allowed to say 12 to the x. You cannot do that. No, 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 no. It's because in PEMDAS, please excuse my dear Aunt Sally, the parentheses have to be done separately. So technically you would have to raise 4 to the x power before you could do a multiplication by 3. So do not put it as 12 to the x, only leave it as 3, parentheses, 4 to the x. All right, there's obviously a typo here. So we're going to look to see if there's a change in the numbers. Oh, not a typo, an extra comma, sorry. Look to see if they're going down by the same amount. So you can try multiplying and dividing the numbers between each other. What's happening here is that we are dividing by 3 each time. If you're dividing by 3, that means you have a fraction for your b value. Okay, so we're dividing by 3, which means 1 over 3, sorry that was loud, needs to go in parentheses, and then your starting value goes in front. That's your equation. Just to show the difference between these two things, because you've got linear versus exponential, we're going to compare these. Talisha has offered 2 pledge options for donating to a charity. Which option will increase the pledge amount faster over time? So option A was $100 in the first week, and each week after that amount increases by $25. So $100 plus a $25 increase from the previous amount. So like 100, 125, 150, you could probably organize this better in a data chart, etc. Option B, I'm gonna do this one as a data chart. $1 for the first week. So week 1, starting out at 0, $1, and each week after that, the amount triples. So after the first week, it's going to be 3. After the second week, it's going to be 9. After the third week, it's going to be 9 times 3, which is 27, and so on. Put this one as a data chart. 100, 125, 150. So what'll happen is you actually start off pretty slow in the exponential growth model, but this is what's going to be really great, because as something grows exponentially, think about the curve. Your curve is going to get larger and larger and larger, faster and faster. So that's option B. For option A, this is consistent. This is a linear pattern. Linear patterns are straight lines. They do rise from left to right, but this is going to be pointing that direction as opposed to the other one is going to be going up to the sky. We want the money up to the sky. So if anybody ever asks you to increase by a certain amount each month or to triple or double your money, always choose the doubling the money.